So today we'll see what is an amplifier. An amplifier is a device which needs a negative feedback to amplify the signals to the required amount. That means we are going to strengthen the signal with the help of a gain. So there are different configuration we can design an amplifier. So there are CB configuration, CE configuration, and CC configuration. The characteristics of all these configurations have been tabulated here. The input resistance for CB configuration is low, about 100 ohms. For CE configuration is about 800 to few kilo ohms. And for common collector configuration, it is high, about nearly around 750 kilo ohms. Output resistance for these configurations are for CC configuration is very high, is about 500 kilo ohms, and for CE configuration is high, about 550 kilo ohms, and for CC configuration it is about 50 ohms. The input current for CB configuration is represented as IE, and in the case of CE is going to be IB, whereas in CC it is going to be IB. Output current has been calibrated as IC for CB configuration, and CE is IC current is going to be IC, where CC configuration is going to be IE. The input voltages are taken between given between emitter and the base, whereas in the case of CE configuration, base and emitter, and for collector configuration between base and the emitter. The output voltages are taken from for CE configuration is going to be C and E, whereas CB configuration it is going to be common base and the collector, and for common collector configuration it is from the emitter and the collector. When you calculate the current gain for CB configuration, we call the current gain is going to be alpha, which is equal to IC by IE, which is less than unity, which is around 0.95 to 0.99. Whereas beta is around, which is for CB configuration, we calibrate the current gain to be beta, which is equal to IC by IB, which is high about 2.5 to 400. Whereas in the case of common collector, the current gain has been represented as gamma, which is equal to IE by IB, which is around high value. You will get a high value. Whereas in the case of voltage gain, next characteristic is voltage gain. It's about 150 for CB configuration is a medium, whereas in the case of CE configuration is about 500, it's very high. Whereas common collector configuration, it is less than unity, which is about medium range. The output signal phase is the next characteristics. It is in phase with the input in the case of CB configuration, reverse in the case of CE configuration is around 180-degree phase shift, will get it, whereas CC configuration is in phase with the input. Next, the applications are for CB configuration we can utilize for high frequency circuits, whereas in CE configuration we can use for audio frequency circuits, whereas in CC configurations can be used for impedance matching. The common terminal leakage currents for common base configuration is available at the base, which is very small, whereas in the case of a common emitter, it's emitter which is very large, whereas in the common collector it is at the region of collector where is very large. So next, this is a configuration how the common emitter, common base, and common collector configurations are represented. I think you have already studied. Now we are going to say that number of stages we go for common design of an amplifiers. We'll see in detail in the next video. To be an power ampli bandwidth. The bandwidth is nothing but the range of frequencies. The range of frequency where you can see that these are the over which the amplifier works effectively. It is usually measured between the lower cutoff frequency and the upper cutoff frequency. Example, for an audio amplifier, it may work from 20 kilohertz, 20 hertz to 20 kilohertz. Next is the input impedance. The input impedance are is the resistance offered by an amplifier to the input signal. High input impedance, which is desirable so that the amplifier does not draw too much of current from the source. Next is the output impedance. The output impedance is nothing but the resistance is seen at the output terminal of the amplifier. Low output impedance is preferred so that the maximum power will be transferred to the load. Next is the efficiency. It is the ratio of output power to that of the input power. How efficiently the amplifier converts the DC power into an useful AC output power. Next factor is going to be a fidelity. Fidelity means the ability of an amplifier to produce the input signal without any distortion. Whereas a noise is nothing but unwanted signal that affect the amplifier at the output is called as a noise. A good amplifier should have a low noise. So next, what we are going to see that we are going to see that what are the classification of power amplifiers. The classification of power amplifiers are nothing but we have power amplifiers. It's a class A amplifier, class B amplifier, class C amplifiers, class D amplifier, class AB amplifiers. So these are the different types of power amplifiers which can be used for the design of an audio amplifiers. Power amplifiers are mainly classified on the base of the Q point. So if the operating point is chosen at the middle of the load line, it is called as class A amplifier. If the operating point is chosen at the cutoff, it is called as a class C amplifier. If the operating point is chosen beyond the cutoff, it is called as class C amplifier. So it conducts for a 360 degree. So this is about the different types of power amplifiers. Next, we will see about what is Class A amplifier. Class A amplifiers, we say that the Q point is chosen at the middle of the load. So this will give you the equal swing on the either side of the direction. Both the halves of the input comes at the output, and hence Class A will give an amplitude distortionless output. It can handle any type of small signals. It's whose efficiency is also very nice. So always we have to depend on whenever we design any power amplifiers, the Q point plays a vital role. So always for a class A amplifier, we have to choose the Q point in the middle of the load line so that it can swing on the either side equally. That is the importance of class A amplifier. This is the graphical structure of an class A amplifier between the current and voltage curve. So this is the output characteristics, and we can see that the Q point is located at the middle of the transistor, middle of the characteristics. You can see that it swings. Below that, we have shown the sine wave so that it is swing equally at the on both the sides of the load line. So next is going to be a class B amplifier. Class B amplifier, here the Q point is chosen near the cutoff, exactly at the cutoff we choose it, so that this will give the swing only in one direction. Whereas in a class A, it is equally distributed on both the direction. Here the swing will happen only on one direction. Only one half of the input comes at the output. Hence, the class B will give an amplitude distorted output. Amplitude distorted output. It can handle very large signal. Its efficiency is very high. Compared to class A, its efficiency is very high. It conducts for 180 degree. This is about the class B amplifier. So you can see the characteristics. You can see that one half you are having a both. Only one half it is showing the red waveform shows that it conducts only in one direction, not on the other direction. So next, class C amplifier. Class C amplifier, here the Q point is chosen at the beyond the cutoff point. Beyond the cutoff point, this will give a partial swing in one direction, not full swing. It is partial swing only. Only a portion of the input comes at the output. Hence, the class C will give the output in terms of amplitude severely distorted output. So it can handle very large signal. So this is about class C amplifier. So the difference between class B and class C is where the Q point is located at the cutoff in the case of class B, whereas class C it is located at beyond the cutoff region. So only you won't get a full swing, you will get only the partial swing. So you can see that it can handle very large signal. It conducts less than 180 degree. It is not exactly 180 degree phase shift. You will never get it. You get only less than 180 degree phase shift. This is the waveform input-output characteristics and the Q point where we have located at the beyond the cutoff, and you can see that the red thing, it is partially conducting. So this is the class C. Finally, we have concluded with the diagram. So it's a class A, class B, class C. So the input sine wave we have given, output you can see that both the direction it is conducting. Whereas the class B, you can see that it is conducting only for the positive half. Whereas the class C, it is conducting partially. So this is about class C different types of power amplifiers. Now we'll see that how the distortionless amplifier can be designed. So out of three amplifiers, Class A is unsuitable as the distortion is very, very heavy. So we never prefer a Class A amplifier. Among the three, Class A is the best, which gives a what? Distortionless output. But Class A cannot handle a large signal as is required by the power amplifier. This is one of the disadvantages of an Class A amplifier. Though Class B gives a heavy distortion, it gives gives the output one half of the input signal perfectly. So and the Class B can handle very large signal. This is the advantage of a Class B amplifier. So now you can use a Class A amplifier as an audio amplifier. We have seen the three classification. Among the three classification, we conclude that Class A is the best which gives output in without any distortion. So that when we prefer a Class A amplifier. Among the configuration, we know that CE is the best as it gives the maximum power. So and the common emitter amplifier will give a high output impedance. Unfortunately, for an audio amplifier, the output device is a speaker which has low output impedance. So that only we never go for CE amplifier. Alright. Impedance matching. The speaker impedance matching is typically about 4 ohms. So hence there is a mismatch between the Z0. Z0 is the output impedance of an amplifier and the low impedance of the speaker. So there is always we have a mismatch between the impedance between the input and the output. This will result, because of this mismatch, we'll get a very low gain. That is, loss of gain will take place. So this can be how we can avoid it. This can be avoided by connecting a transformer at the output. So this is only one solution where you can get a perfect impedance matching between the input and the output. The primary winding will match the high input, the high Z0. Z0 is already I told that Z0 is output impedance of an amplifier, while the secondary will match the low impedance of this speaker. So what happens if you do all these things? A proper impedance matching will occur so that the maximum power transfer will take place from the input towards the output. So this is the final Class A audio amplifier which has been designed. You can see that this is a common emitter. This is a common emitter we have used. So what are the drawback you can see in this design is it cannot handle a very large signal. Already we told it. And in Class A amplifier, the operating point is chosen around the middle of the load line. So if the signal exceeds the cutoff point, the output current stops at with no current you can see beyond this cutoff. And any signal with a lower amplitude will not come in at the output itself. This is the one of the. Similarly, if the signal exceeds the saturation point, the output current cannot increases furthermore. So even if the input signal increases, the output signal never increases. So this is the Class A amplifier. You can see that when it goes beyond the cutoff and below the cutoff, the signal gets what blocked. You can see that the peak has been slicing of signals have been taking place. What it means that beyond that, no current will flow into the circuit. So Class B push-pull amplifier. Class B push-pull amplifier is mainly used for designing an what amplifier, high power amplifiers only. So we can use this, which has a greater signal handling capacity. We can, if there is any problem of handling the higher signals, we can prefer this Class B push-pull amplifier. But Class B will give only one half of the signal, already we told it. Hence, we can use two Class B amplifiers. So one for the one half and another for the other half. So this type of an amplifier is called as push-pull amplifiers. So this is a design of a push-pull amplifier. You can see that there are two transistors we are having. We are called as a TR1 and TR2, or the output transistor, which is connected back to back with their emitters grounded. The output transformer TR1 couples the push-pull output of push-pull output to the speaker. In the push-pull arrangement, T1 conducts for one half of the signal and T2 conducts for the other half of the signal. So this is how the push-pull amplifier works, and it conducts for both the half cycles. So the driver transformer TR2 gives a two out of phase signals, and during the one half, the positive half of the signal transistor 1 will be conducting for the forward, so that it forward biases at T1, while the negative half reverses the will produces a reverse bias to the transistor T2. Thus, when T1 conducts, T2 is cut off, and vice versa. So this way, both the transistors will be conducting alternatively to give a full swing of output. Next is going to be your class D amplifiers. So during the positive half cycle, Q1 gets forward bias and it starts conducting. During the negative half cycle, Q2 gets forward bias and it starts conducting. Thus, both the transistors conducting alternately. The output, the amplifier works for 360-degree in the case of class D amplifier. Hence, we can find out here we can get rid of the distortions. So 100% efficiency you can achieve. This is the working of a push-pull circuit. During the first half, T1 conducts. This is the transistor T1, T2, whereas the next half, the transistor T2 will be conducting. So during the first half, the collector current flows from the center tapping through the transistor T1 to the ground. So this half is coupled to the speaker through the transistor TR1. You can see that the transformer TR1. So this is called the working of during this second half of the signal, transistor T2 starts conducting. IC current flows through this under tapping through T2 to ground. So this half is coupled to the speaker through the transformer 3R1. So what are the drawbacks? We can see that though the circuit is functions well, it has a few drawbacks. What are the drawbacks? It affects the quality of the output. Phase shifting circuits must both these drawbacks can be avoided if you use one pair of PNP, another one is going to be an NPN transistor. So the drawbacks they have given. So what they drawbacks? The transformer coupling affects the quality of the output, and phase shifting circuit is must. So in order to achieve this, what they suggested that, so we can go one transistor to be a PNP transistor, another one is going to be an NPN transistor at the end. This is called complementary symmetry amplifier. Here they covered the drawbacks. They overcome the drawbacks what they have facing in the push-pull amplifier. So one they are using an PNP, another one is going to be an NPN at the output stage. So we'll see that this circuit used one NPN transistor and one PNP transistor during the positive off cycle T1, that is called NPN base, gets forward bias and it conducts while T2 PNP gets a reverse bias and does not conduct. This gives one half of the signal at the speaker coupled to the emitter. We can see that during the other half of the signal, T2 gets forward bias and conducts, while T1 gets reverse bias and does not conduct. Thus, T1 and T2 conduct alternatively, giving a distortionless output. This circuit does not require any phase shifter. This is called the advantage of complementary push-pull amplifier. So next we'll see that what is crossover distortion. We'll see the design. So class B push-pull amplifier has one limitation. What is that limitation is? As the phase of the signal changes from positive to negative or negative to positive, one transistor stops conducting while the other starts conducting. But the transistor cannot conduct instantaneously because as it requires a minimum VBE before it starts conducting. So it requires, so one transistor starts conducting, another means there is a gap is overlaying between the starting period. So it requires a minimum VBE to make the other transistor to move into a conduction period. So thus that gap is called as crossover. That is called as a distortion, where the distortion occurs here. This distortion is called as crossover distortion. This is called crossover. You can see that one half is conducting, when it starts conducting for the other half, there is a small gap there. So the starting period we require VPE 0.7 volt or 0.3 volt we require to make the transistor to move into a conduction period. This is called the crossover distortion. So next is going to be the class B AB amplifier. So this circuit overcomes whatever the problem we have faced in the previous analysis. That is called crossover distortion. biasing is done such a way that even if there is no input signal, a small current keeps the output transistor conducting. So this is the advantage of class AB amplifier. The circuit uses two diodes whose characteristics matches with that of the BE junction, base emitter junction of the output transistor. Biasing the transistor R1 and R2 are also identical values. Whatever the transistor they are using, that R1, R2, you can see in the design, they are an identical transistor. So, and also they have used two diodes so that this diodes overcomes the crossover resistance, that gap, that I mean changeover from one conduction of one transistor to another transistor. They fill with the the diodes what they have used, so that they get perfectly matches with the conduction. There is no time gap. You can see at the symmetrical components. So here what we're going to use it, there are, since the resistance R1 and D1 are identical and to R2 and D2, so the diode junction as well as the output point will be half the supply voltage. Because of this symmetry, both the transistors T1 and T2 will conduct equally when even when there is no input signal, there will be a current ICQ, so that it will be equal to half of Vc minus 0.6 by R1. This will keep the output transistor conducting. So this is the process of how the elimination of crossover distortion we can go for it. So the elimination is we are using two resistors and two diodes so that the switchover time will be compensated. So next is going to be your thermal stability. Thermal stability says that in addition, the two diodes will also provide a thermal stability. So they prevent the output transistor going to a thermal runaway. And also we can see that the output current is high, heating dissipation is more, and the increase in temperature produces more charge carrier in the base emitter junction. The increase in IV, hence IC, this in turn increases the power dissipation and hence the heat, and this chain goes till too much current flows and destroys the transistor. This is called thermal runway. So this is arrested by the diodes in the output circuit. So the thermal runway problem can also be arrested because of this diodes which is used at the output of the transistor. So when the charge carriers increases in the base emitter, the junction T1 of T1 and T2 at the junction, a small increase takes place in the diode. What are the diodes we have used? D1 and D2 due to mismatching. Due to matching characteristics. This increases the diode current and produces more drop across R1 and R2 and brings down the forward bias at the base of the transistor T1 and T2. So thus two diodes prevent the crossover distortion. Finally, what they say is that time gap, that small time gap is being overcome with that is called as crossover distortion. That crossover distortion can be avoided with the help of two diodes, which as well as it provides a good thermal stability in the circuit. This is about the power amplifiers. So next we are going to see about interstage coupling. So we must know before going in depth with this interstage coupling why we go for interstage coupling. The interstage coupling we use for increasing the gain of the system. So here the AC output signal from the common emitter stage can be coupled to one input of the next stage either by means of transformer or by a resistance capacitance combination. So from this we are going to say that if I want to couple one stage with the other stage, we can connect it through transformer or by resistance capacitance combination. This is the meaning of the first sentence. The maximum power gain will be obtained with the transformer having a suitable primary to secondary step down ratio to match the output resistance of the first stage to the input resistance of the second stage. So the main motto is to go for maximum power gain. So this can be attained with the help of a transformer. The turns step down ratio will be typically between 5 to 10 to 1. The transformers, however, they are relatively expensive components and are also susceptible to magnetic pickup. So accordingly, they are rarely used in low-level transistor amplifiers. We know that the transformer coils are bulky. It is very difficult to handle that. And also it is it is more expensive component also. So what we are going to, and also one more difficulty is magnetic pickup is there. So it is more susceptible to magnetic pickup. So so because of that reason, it has been rarely used in low-level transistor amplifiers. So with the help of this, so the another possibility is we can go with the resistance capacitance coupling. Here the input resistance of the second stage effectively coupled to the load resistance of the first stage, so that the input resistance and the load resistance of the first stage will remain same. So the voltage gain will be equal to the current gain, and the power gain will equal to the current gain square of the current gain. So if the current gain is 50, the power gain will be square of it, that is going to be 2500. That is, it's equivalent to, in terms of decibels, it is around 35 dB. The effective AC load on the transistor consists of several components in parallel with the load resistance RL. So the output resistance of the transistor, the base bias are called transistors called R1 and R2, and the input resistance of the next transistor. The only useful part of this load is the input resistance of the next transistor. The other components are all present loss, and when evaluating the overall gain of the transistor amplifier, it is necessary to take the losses into account. So what they say is that the effective low AC load on the transistor being connected to the several components such as a load resistor, output resistance, and base bias resistors called R1 and R2. Along with that, we have an input resistance. So the useful part of this load is the input resistance to the transistor. The other components all represent its minimum loss only. So the value of coupling capacitor depends on the required low frequency response of the amplifier. So when you select a coupling capacitor, it should always depends on the how much frequency response of the amplifier, whether it is high or low, we have to calibrate it. According to that only, we have to go for using a coupling capacitor. As the signal frequency is decreased, a point will be reached where the amplifier gain starts to decrease due to increase in impedance of the coupling capacitor. So the gain will fallen below by 30%. That is called 3 dB at the frequency at which the reactance of the coupling capacitor will be equivalent to the total resistance in series with the load resistor RL. So this series resistance will be equal to the load resistance of the previous stage plus the input resistance of the next stage, so that I can achieve a maximum power gain. So this is the structure of a resistance capacitance coupling. You can see that there is one transistor, the second stage transistor have been coupled by a capacitance cap. So the coupling is mainly used for so that proper transferring of signals will be transferred from one transistor to another transistor. So that the main motto is to achieve a high gain. So the value of the emitter resistance, here we have used emitter resistance, which is called RE, which has been decoupled with the capacitor C2. So they also depends upon the required low frequency response. The gain of the amplifier will fall below 3 dB at a frequency at which the reactance of the capacitance C2 will be nearly equal to the emitter resistance, which is shunted by the resistance represented by the transistor. So when we calculate the total the output resistance of the transistor in a common collector arrangements, it will be equal to Rg plus Rb into 1 minus alpha. Rg is in parallel with the load resistance RL, which is in parallel with R1 and R2, and this is around, so the Rg, if you consider to be 1670 ohms, means it gives a transistor input resistance approximately of about 40 ohms. So the required capacitance for the 3 dB which fall in gain at 25 hertz will be equivalent to 150 microfarad. This is how we go for calculating the coupling capacitance value. So next we'll go with the gain control. This is the circuit for the gain control. You can see that there are two transistors. The same circuit, this resistor which is used at the base are mainly used for proper biasing. So in order to get a proper stability for the transistor, we go for this thing. And this is an to the first transistor we have connected a potentiometer, so we can vary this potentiometer to go for adjusting the gain value. So the gain of the transistor amplifier can be adjusted by making the coupling network between the stages a variable attenuator. So between stages, they still acts as a variable attenuator. So the attenuator, what is the meaning of an attenuator? It attenuates certain range of input signal. So the attenuator must be designed so that it has a negligible effect on the frequency response of the network. So we know that the attenuator fully depends on the resistive network. So the attenuator must be designed so that it does not have any effect on the frequency response of the network. So the DC operating point of the either of the transistors shows us two suitable methods of control. So it is shown at point A. You can see there are two potentiometers have been used. Though at point A, which is available at the base of the transistor Q2, is probably better and it is most widely used. It has no effect on the biasing setting and does only have a slight effect on the low frequencies. It does not have a biasing stability, and also you can see that there is a slight, it has only a slight effect on the low frequency response. The control shown at B, there is another potentiometer which has been shown at a point B. It has no effect on the low frequency, but there is an but it will alter the DC voltage across the first transistor. So it will change the DC characteristic of a transistor, first transistor, but it does not have any effect on the low frequency response. So this is next is going to be a frequency response control. In audio amplifier, the control of frequency response is usually referred to as tone control. In the case of audio amplifier, we know that the control, if you want to change, if you want to control the audio amplifier to in such a way that the frequency response is usually it mainly the amplifier, audio amplifier, we can control the frequency response so that it is usually referred to as a tone control, and it is used to attenuate the response at low or high frequency and end of the frequency band. What it means that so the frequency response plays a vital role so that it is been used for controlling the tone value, that is called which may attenuate the frequency at the low frequency or may have a frequency attenuation. It may takes at high frequency also at the end of the frequency band. So the control can be carried out by incorporating a frequency dependent circuits in the coupling network between two stages. So increasing the effective capacitance in parallel with the load resistance of the transistor will reduce the high frequency response. One is so we can increases the effectiveness of the capacitance by connecting this capacitance in parallel with the load resistance of the transistor, which will reduces the high frequency response. And by varying the effective capacitance in the coupling circuit will reduces the where the low frequency response can be controlled. These are the two ways I can do it. One, by increasing the effective capacitance at near the load resistance, that is the high frequency response, and by varying the effective capacitance in the coupling circuit will control the low frequency response. This is how we select the capacitance so that it takes the two actions. So a typical arrangement has been shown here. The potentiometer P1 controls the low frequency and the potential P2 will control the high frequency response. You can see here. This is how we do with the P1 and P2, how it is adjusting the frequency response, or it is controlling the frequency response at low and high mode, right? So this is the circuit tone control. So what is the use of a negative feedback? So the negative feedback is mainly used for loss of gain. Stability you can achieve in gain. Internally generated distortions can be reduced. This is the third factor. This can be applied from the output to the input of a single stage or alternatively over several stages. You can go for any multiple stages, you can go for it. But what is ultimate gain? We have to get a stability in gain. So there should not be any loss of gain should take place. So this is a application of negative feedback over a single stage. They have used only single stage for this reference. Like that, I can connect to many transistor, many single stage can be cascaded. Right, this is the transistor, we have it. So this is a common emitter amplifier with a negative feedback we have given here. You can see that there is a negative feedback from the collector to the base. So through the resistance called RF and or by including any unbypassed resistor RE in the emitter circuit. You can also connect a capacitor near the resistance also in parallel to it, or by connecting RF between the collector and the base also you can connect. So the lateral is used very useful for, and is commonly. So normally we use for use a bypass capacitor in parallel with the RE. This is a usual way of designing an a single stage amplifier. So in multi-stage amplifier, the feedback may be introduced in series with the signal source. That is called either it may be a current feedback or series feedback, or it may be a parallel feedback. So or we can call it as a shunt voltage feedback or current feedback we can give it. In series feedback, we call it as a current feedback. Here the signal is deployed across the resistor RE, developed across the resistor RE in the emitter of the second transistor being fed back to the base of the first transistor. Whereas in the shunt feedback, the signal appearing at the collector of the second transistor being fed back to the emitter of the first transistor. This is how we go for, so here we are applying at the second shunt feedback, we are applying to the emitter, whereas in the series feedback, we are applying back to the base of the transistor. This is how the shunt and series feedback plays a vital role in the connections. This is the shunt and series feedback network. You can see that how it has been applied here. In series, we told that it has been fed back to the base of the transistor. Whereas in the case of shunt feedback, it has been applied to the emitter of the transistor. So this is the connection of an current and series and current of series current feedback and shunt voltage feedback. Next topic is going to be your low noise consideration. So what is low noise consideration? So here we talk about the noise figure. What do you mean by noise figure? It is a ratio of signal to noise ratio power to that of the output signal to noise ratio. So in the case of an ideal amplifier, what we have to amplify the incoming signal on the noise without changing the signal to noise ratio. This is a motto. That then means the noise figure ratio should be equal to unity. Then means in terms of if again we speak it, it should be around 0 dB. So, but in practice, it won't happen. There may be a plus or minus errors will be there. So, in practice, some extra noise will be generated within the transistor. Or so, what about the noise figure? If there is a extra noise is being added in the transistor, the noise figure of a transistor amplifier will always maybe greater than the unity. Though so, nearer the noise figure is equal to unity, the better will be the amplifier. What they say is that if the value is very closer to unity, then the amplifier is a better amplifier. If it is not, then we can have to go for alternative solution to make the noise figure is equivalent to unity. So what are the requirements we suggest for an audio preamplifiers? What do you mean by preamplifier? First we should know the definition of a preamplifier. It is an electronic amplifier. It removes the signal from the detector without considerably degrading the intrinsic signal to noise ratio. What they say is that the amplifier that removes the signal from the detector. The detector is nothing but a receiver. So we have to, in the receiver, we get a modulated signal. From the modulated signal, we have to segregate our original signal without considerably changing the signal to noise ratio. This is the definition of an preamplifier. Preamplifier features mainly include tone control, digital inputs of versatility, and balance adjustment. These are some of the features we prefer for the preamplifiers. These amplifiers are uh, normally used in home theater and home stereo systems. These where we can apply this preamplifiers. So these are mainly designed to use an audio signal from the audio source device and amplify it to a level that can be further processed through an power amplifier so that it play through the speakers. So finally we send it to the speakers. So we amplify it and further we pass it through an power amplifier. So sufficient amount power will be we gain for the signal, and then we make play through a speaker. Finally we send it to the speaker. This type of amplifier are also responsible for processing the audio signal, like adjusting the tone, balance, and volume. These things where we can use this audio preamplifiers. So what is the working principle of preamplifier? So this works by changing the weak electrical signal to a strong output signal. So where the noise tolerant and the strong enough for transmitting the power to a power amplifier as well as the loudspeaker, which is known as the preamplifier, or simply we call it as a preamp. So what is the definition says that working principle is converts the weak electrical signal to a strong output signal which have a very less noises, and they are very strong for transmitting to a power amplifier so that it will be lead to a loudspeaker. So the final output signal would be distorted or noisy without using this amplifier. If I didn't use this amplifier, the output signal will be noisy signal. So it is better to use a preamplifier before sending to a power amplifier. Preamplifiers are used in home stereo systems, and we told that it can be also used in home theater systems, but the choice of this amplifier mainly depends on various factors like the number of required channels and the preferred features and sound quality. So this is the preamplifier circuit. It's a simple circuit which is provide around the 3 to 30 voltage gain, and it mainly depends on the source as well as the load impedance. It depends on both the source and as well as on the load impedance. So this is the preamplifier circuit. So the required components which is made to design this preamplifier, it includes a resistor, two resistors, two capacitors. These are electrolytic capacitors around 10 microfarad, and the voltage is around 10 volt, and the NPN transistor we have uses. So the power supply, normally we give a power supply to the collector terminal of the transistor. Here the capacitor C1 is in zero signal condition, works as an open circuit since the capacitor reactance is infinite at zero frequency. At zero frequency, the reactance of the capacitance C1 will be zero, will be infinite at zero frequency. Therefore, capacitor C1 works as a blocking capacitor. What they say is that at the zero frequency, if the reactance of the capacitance is infinite, then the particular capacitor will act as a blocking capacitor. So next, similarly, we have another capacitor called C2. The capacitor function is similar only, but this capacitor C2 will work as a coupling capacitor and feeds a signal, amplified signal, to form the output voltage. The simple preamplifier circuit utilizes the fixed bias circuit. Fixed bias circuit. Here we are not using a potential divider bias. Here we are using a fixed bias, so that the zero signal process can be established by choosing the resistance R1. This is how we design the preamplifier for doing its working action. So there are three different types of preamplifiers we have. One is the current sensitive preamplifier. The current sensitive preamplifier with 50 ohm input impedance provides the correct termination of about 50 ohm coaxial cable. It's a 50 ohm is nothing but the characteristic impedance, and changes the current pulse to a voltage pulse from the detector. What it happens here? Here this current sensitive preamplifier which converts the current pulse into one voltage pulse from the detector through a coaxial cable of 550 ohms. If the increased time of the amplifier is small as compared to that of the detector increased time, then the preamplifier voltage gain is A, and the voltage plus pulse amplitude at the preamplifier output will be given as V out is equal to 50 IN. IN is nothing but input current in amperes. So this is how we calculate the output voltage. So what they say is that if the increased time of the amplifier is small, uh, due to the increased time, if the amplifier voltage is very small as compared to that of the detector increased time, then the preamplifier voltage gain will be A, and whose output voltage can be estimated as 50 into total input current IN, right? Where IN is the current pulse amplitude from the detector, so the signal is fit to a faster discriminator for counting the application. For counting application, we use it whose output is recorded through the counter timer circuit. This is an application of a preamplifier. So this is the circuit of current sensitive feedback. You can see that this is a current pulse we have given it, and this has been given to an amplifier whose gain is going to be A, and there is a 50 ohm resistance are being connected to the input of the transistor amplifier, and we are going to find it out the output, right? So the dominant limitation of the timing application on time resolution through a photomultiplier tubes or microchannel plates is a variations within the transit time of the electrons when they cascade throughout the detector. So this can causes a jitter within the pulse arrival time at the output of the detector. What they say is that if the limitation for timing applications, since we told that it can be used for timer control application, if I use for a timer application, we are very dependent on the timing resolution. To either through a photo multiplier tubes or micro channel plates. So within the transit times of the electrons, when they cascade throughout the detector, so they can cause us a jitter in the pulse arrival time because of multiple channel. If I'm going multiple photo multipliers tubes, if I'm going to use it, multiple tubes if I'm use it, or any multiple plates if I'm going to use it, so they causes a there is a variations in the arrival time of the electrons since they have been cascaded throughout the detector. So because of this variation in the transit time, they causes a jitter in the arrival of output. The arrival time will be different at the output stage of the detector. But if the detector signals are sufficient to need a current sensitive preamplifier, then the preamplifier input noise effect on the time resolution should also be considered. So this type of preamplifiers are mainly used for timing applications. So this if there is any variations, if I suppose if I'm going to use a preamplifier, so this kind of current sensitive preamplifiers if I suggest it, so that the noise effective on the time resolutions can be reduced. So this is how our preamplifier has been used for timing counter applications. Next is going to be a parasitic capacitance amplifier. What do you mean by parasitic capacitance amplifier? So this amplifier, which has an impedance of about 5 mega ohm at the input side, is known as a parasitic capacitance preamplifier. So what this is, total impedance is around 5 mega ohms. In the case of preamplifier, then that type of capacitance effect is called as parasitic capacitance preamplifier. So the generated current pulse by the detector is incorporated into the combined parasitic capacitance available at the preamplifier input and the detector output. So the combined parasitic capacitance will ranges will from 10 to 15 picofarad. So this resultant signal is a voltage pulse with the amplitude that is proportional to the whole charging within the detector pulse, and the rise time will be equal to the period of the detector current signal. So what it says that since it is having a high input impedance, though it produces a capacitance parasitic capacitance effect. So the current pulse which is generated by the detector, it has been incorporated into the parasitic capacitance which is available at the preamplifier. So I'm putting the or I'm sending the current pulse which is from the detector circuit, and I'm sending it to the preamplifier which has an input impedance of 5 mega ohm, so that it causes a parasitic capacitance effect. And so the ranges of capacitance effect which I can get it around to be 10 to 50 microfarad ranges I can go for it. So the resultant output of the amplifier is the voltage pulse. It is not a current pulse, it is a voltage pulse. It has an amplitude which is proportional to the charging which is taking place in the detector pulse, and also the rise time which is equivalent to the period of the detector current signal. This is called as a parasitic capacitance preamplifier. You can see that this is a detector cathode, this is the anode, this is the parasitic capacitance. You can see that, and it has been given to the amplifier. So this is how so here the input impedance and the resistance are connected in parallel, which causes a because they are act as a RC network, right? So the charging of a capacitor will undergo an exponential decay of the signal with around approximately 50 microseconds constant. So what will happen? The amplifier with a unity gain or a high input impedance is incorporated as a buffer to drive the coaxial cable, which has a very low impedance at the output. So here therefore about 93 ohm resistor with the output in series in the output, you can observe the reflected signals are within the long coaxial cable by ending the cable in its characteristic impedance. This type of parasitic amplifiers or preamplifiers are utilized within the semiconductor detectors due to high sensitive gain to the little changes in the parasitic. Even if there is a minute changes in the parasitic capacitance causes a very big changes in the gain. So this detector capacitance for partially depleted semiconductor detectors with changes in the applied bias voltage to the detector diode. So this is a small movement can adjust the input capacitance with a few tens of picofarad. So what ultimately they say that even a small variations, if I give it to if it happens in the parasitic capacitance, it causes a greater effect in the variation of the gain. So you have to see to that how partially, I mean, how the detector changes is applied bias to the detector diode, so that the interconnecting cables will have a small movements can adjust the input capacitance with a few tens to picofarad. So next is going to be a charge sensitive preamplifier. So what does it mean by charge sensitive preamplifier? It is also a type of preamplifier that frequently it has been used in the circuit mainly for pulse detectors. For any pulse detectors, I can go for charge sensitive preamplifiers. So it has been designed to provide high stability, improves the stability, and also low noises, and their integrating nature offers an output. So while integrating it, you can get a better output. So that's the output will be proportional to the whole charge applied from the detector throughout the pulse event. So the entire output depends on the how much charging has been supplied from the detector throughout the pulse. Throughout the pulse, how much charge I'm applying it. That will say that whether the output is increase or decrease. So when compared to the other preamplifiers, the gain of the preamplifier is stable. So we have seen parasitic capacitance amplifier, pulse I mean preamplifier. Either you can give us a current feedback amplifier or negative series feedback amplifier, like that we can give it. So compared to those preamplifiers, here the gain of the amplifier is very stable. It does not depend on the amplifier bandwidth or the input capacitance. So these type of preamplifiers are normally used within the radiation detection application. Where I'm using it in the case of radiation detectors, we can go for this applications. So this can be installed within the home audio systems and can be combined with audio equipment. It also been used in the home audio systems. It is very cheap and can generate a natural sound effect. This is the charge sensitive type. You can see that the current charging period we have given it. Feedback is going to be the capacitance. How this current pulse is going to charge the capacitance, and what is the output I'm getting it. So current is the input, output is going to be the what in terms of voltage we are going to find it out. So the difference between a preamplifier and an amplifier. So it is a preamplifier is an electronic device which is used to prepare an audio signal for amplification or for recording purpose. Whereas an amplifier is an electronic device which provides an what power supply to a headphones. So it is used for recording purpose. It is used for it has been used in the headphones or speakers. It is also known as a preamplifier. It is also called as an amplifier. Third one is going to be your they are being found preamplifiers are found in always in an integrated amps or AV receivers. So whereas in the case of amplifiers which can be used in transmitters, TV transmitters and receivers, radio, microcomputers, high fidelity stereo equipment, digital equipment and musical instruments. Here the preamplifier cost is very low, but in the case of an amplifier it is low to moderate. Preamplifiers has a very various inputs and single output. It has a multiple inputs and single output. Amplifier is a single input and various amplitude I can get it right. It has a fixed gain setting, whereas an amplifier do not have any type of fixed gain. The preamplifier contains a fixed input impedance, whereas the input impedance is fixed or adjustable. It does not have any tone control in the case of preamplifier, but it has a greater control over the tone. So the preamplifier has two audio channels. Here we can have we can lead up to 7 channels in the case of amplifier. So the next is going to be your operational amplifier. The operational amplifier is which is available. We can design this operational amplifier, or it is available in the form of integrated chip. So it is a versatile device where we can go for any DC and AC applications. It amplifies the difference in voltage between the two inputs. That is one of the advantage of this operational amplifier. It was developed to perform the arithmetic operation, amplifier, buffers, comparators, filters, everything I can go for. This is a representation of an operational amplifier. It has an inverting terminal, non-inverting terminal, and two supply voltage and one output. So this here the output of an voltage amplifier, operational amplifier can be defined as V out is equal to AOL into V plus minus V minus. V plus is nothing but positive voltage. V minus is now going to be a negative voltage. We told that already this takes only the difference in input voltage will be amplified, where AOL is nothing but the open loop gain of an amplifier. So it has a 3-terminal device. It has consists of high input impedance and the output is very low output. One of the input terminal, I told that it's called as an inverting. Another input terminal has been represented as positive sign. The third terminal represents the operational amplifier as an output port. That is the 6th pin. So it has been used operation amplifier here multiple. Here the output is we told that the gain is nothing but the ratio of output by input. Suppose if I'm going to give one, if it is going to, we normally say that V naught is equal to A into Vd. Vd is nothing but differential input voltage. If one of the input voltage is 0, another is going to be in 1 volt, and so the difference is going to be 1 volt. If the gain factor depends, we told that V naught by V in, we told that. And also the gain of an inverting amplifier, it depends on the feedback resistance and the input resistance. I can write that gain is equal to minus Rf by R1 in the case of inverting terminal. In the case of non-inverting terminal, it is going to be 1 plus Rf by R1. So when I multiply it, you can say that 1 volt, if the gain is going to be around 10 means minus 10 volt. If the gain is around Rf by R1 ratio is 10, then the gain of the inverting terminal is going to be minus 10 volt. I'll get 10. I'll get it. Whereas in the case of non-inverting terminal, it is going to be 1 plus Rf by R1. So Rf by R1 ratio is going to be 10 plus 1 is going to be 11. 11 into differential voltage is going to be 1 means I'll be getting 11. So for non-inverting amplifier, the gain will be more. For the inverting terminal, the gain will be less. So the negative terminal sign indicates that there is a 180-degree phase shift between the input and the output. So these are the ideal characteristic of an op-amp. The op-amp, it has an infinite loop gain, and the input impedance is infinite, and it has a zero input offset voltage, infinite output voltage range, and infinite bandwidth. Output impedance is almost very less, zero noise, infinite common mode rejection ratio, power supply rejection ratio is infinite. So it has an the input impedance is in the range of mega ohm or more. An open loop gain over about what you can get around 1 lakh, right, approaching above in some time. So this is approximately they are saying it. And an output impedance is of about less than 100 ohms. So this is the key operation of an op-amp with the feedback. You can see that there is a feedback is available. So there are tuning circuits have been used in the inverting and non-inverting circuit. So an impedance is connected between the inverting or minus input on the ground. The ratio of the feedback impedance to the ground impedance determines the. Normally when I give a feedback, I never go for open loop gain. Since the circuit is closed, we'll call it as the gain is nothing but a closed loop gain. To realize the gain of 10 or 20 dB, the value of the feedback resistor must be 10. Always the feedback resistor is considered to be 10 times greater than the input impedance. So this is how we go with the fixing of RF feedback value and the input resistance value. So this is called the TAA300 integrated circuit. This is for used for an audio amplifications. You can see that this is the common this differential amplifier, and we can have a common PNP transistors and common emitters. So we have an input stage, buffer, output stage, and in between that we have one driver stage also, right? So it has consists of, you can see that the transistor Q1 and Q2 will act as an input stage, whereas the driver stage are Q3 and Q4. Q3 and Q4 are the driver stage. So these are the stages have been used for designing an audio amplifier. In order to reduce the collector DC current of the driver transistor, the output transistor must have a large current gain. Therefore, the two transistors have been cascaded in structure we have used. So that since it has been used in cascaded form, we can achieve a large current gains. The output voltage is limited only by the knee voltage of the transistor that has been controlled by Q10 and Q11. So the driver stage, we told that there are two NPN transistor which is called Q4 and Q5, which has been connected in cascade. So the DC coupling between the input stage and the driver stage is by means of PNP transistor Q3. So how we are connecting one stage with another? By means of a transistor Q3, that is called P. So I'm using my DC coupling by means of a transistor PNP. So the voltage gain of the driver stage is high, and therefore this stage is used to cut off the frequency above the audio spectrum by means of small integrated capacitor C1 which has been inserted between the base of the transistor Q4 and its collector. So what we are inserting between the base and the collector, a small capacitance we are introducing, so that the voltage gain of the driver stage will be maintained high, and therefore this stage is used to cut off the frequency below the audio spectrum. If there is any frequency below the audio spectrum, it will get cut off. That is why we go for using a capacitance between the base of the transistor Q4 and the collector. The voltage gain of the driver stage will be about 200. So here we can say that the gain figure in combination with the collector base capacitance of 10 picofarad makes the capacitance between the base of Q4 and the earth is about 2000 picofarad capacitance. I can use it. So if there is any feedback, without a feedback, the upper frequency is limited. So if I'm not using a feedback, the upper frequency will be limited around 3 kilohertz. 3 kilohertz. Whereas the diode D4 and D5 are connected in series with the resistor to decrease the current of an op-amp of the transistor of a PNP transistor Q3 and to stabilize the collector current of Q4 and Q5 against the temperature variations. So why we are using a D4 and D5? It has been used to go for a proper stabilization of collector current so that it flows into the transistor Q4 and Q5, so it will not get affected due to temperature variations. So next is going to be your 1 watt audio amplifier, which is where they are using a class B amplifier. This is the design of class B amplifier. With the TA300 we are using it, that IC we are using it for designing an audio class B audio amplifier. So it is an the total power here. Why it has been given as a word called 1 watt means the output power will not exceed more than 1 watt. The sensitivity and the input impedance in this case should be such that the maximum output power can be obtained with the input to any ceramic pickup element or any detector in a portable radio. So the other requirements of the circuit should still operate at the half the nominal supply voltage, and the total current drain will be very low. So the complete audio circuit should be compact and easy to mount and must have a low noise and reasonably low distortion factor. So with the TA structure IC, I'm connecting all these things so that it gives a proper load balance to the loudspeaker so that we can able to hear the audio signal. To meet these requirements, TAA 300 has been especially developed. It contains a silicon chip of 2 millimeter square, on which 9 planar NPN transistor, 2 PNP transistor, 4 diodes, 14 resistors, one capacitors are integrated. It has been already shown in the previous circuit. So based on that, we are connecting an external component so that proper audio amplifier has been designed. So next is going to be a TAA 320 IC. So this is a monolithic integrated circuit. It consists of 3 components. One is going to be a MOS transistor of P channel enhancement type and an NPN silicon transistor and a resistor. It has been shown. There is a MOSFET, there is an PNP transistor has been used here. NPN transistor has been used along with the resistor. So here proper biasing can be produced by the resistor or so that the MOS is going to set in a proper biasing operating point. Since the transconductance is proportional to the resistance, since the transconductance is proportional to the IS is nothing but the input current, the resistor must be small as well. So in order to make this proper proportional between the transconductor and the current, the resistor R1 you have to choose it such a way that it should be small enough to obtain a maximum gain. On the other hand, a low value reduces the amplification of the transistor. So that you must be very careful in choosing the resistance value. So the value should be around 1 kilo ohm should be an optimal for overall transconductance of the whole integrated circuit. The TAA 320 has an advantage. It can combines a high transconductance with the high input impedance and low noise value. This is a